All right, in this one, we're going to look at how much energy was lost as the ball hits the ground each time the ball is slammed. And we're going to do this for the flat ball and elastic ball. And you can see that this third tab, flat ball force, this is the data from the force plate as the ball hits the ground. All right, so if we plot this, we see a bunch of spikes. So the first thing we want to do is kind of come in to one of these spikes and maybe zoom in a little bit. And what I'm going to do is just go to this axis, and I think it's going to be about 0.3, something like this. So maybe 0.2. So 0 to 0.2, we have the force response of the flat ball hitting the ground. Let's do the same thing for the elastic ball and check out the difference here. So time versus force response from the plate. All right, and I'm going to adjust the axis here. This one probably goes around like 0.06. Let's go further out, 0.9. Okay, cool. So this is the force response from the elastic ball hitting the plate. And compare that with the flat ball. You see a much different shape, right? And we could probably take this out and go to 0.08. Cool. All right, so elastic ball and flat ball. You can see that the flat ball has a ton of, say, impulse, force over time, right? It's front loaded, and at the end, we see this like trail of basically less and less force, right? The elastic ball, it's more symmetric. You see, like there's still this extra impulse coming from the first half of the collision, and kind of a different shape on the last half. Okay, so we need to find the energy coming in and the energy leaving, right? And all we have is force over time. So what are we going to do? Well, we have a formula that says the force times the change in time is equal to the change in momentum, right? We have F, this equation, let's write it down here. This is F times dt is equal to m times change in velocity. And this thing comes from the fact that F equals ma, right, is F equals m times delta v over delta t, right? So let's just kind of use this as this idea real quick. We can do delta t here, right? Delta t, that equals this minus this, and that should be a constant since we're capturing this data at a constant rate. We have some mass, that's 5.5 kilograms about, right? And then we'll have a change in velocity, right? And that's the trick, right? We need to find this change in velocity just using force data. Ugh. So we're going to make this assumption. We're going to assume that 1/2 of the time the ball is in contact with the ground we have a change in velocity that has some initial velocity and a final velocity. All right, we'll call this thing initial velocity v0 and final velocity vf, right? Now, for the first half, we know that the incoming velocity v0 is some number, and the final velocity, like for the first half of the collision, this is when the ball is hitting the ground, and for half of this time, it's all being compressed, right? We're going to say that the vf is 0, all right? So in the first half of this collision, it comes in with some velocity, and then we get to a velocity of 0 for our v final. And then for the second half, we have a velocity that starts at 0, the ball is compressed, and it's in the middle of our contact time, and then our V final is some number. Okay, so from this, right, we get this other idea. What if we take F dt, so the integral of this force over time, from 0 to half of the collision time, which if we look at this data, it's about 0 to 0.06. So if we do that, say first half of the collision, we have force times the change in time. So that's kind of the integral right here of the 0 point, and then we'll do the same thing. This is force times the change in time plus our previous force, and we're going to sum all the way to 0.03 here. Okay, so this right here is the integral from 0 to 0.03, right? And if this is what do we say? This is f dt, right? First half f times dt, and that's actually we'll write sum of f dt. Okay, so then what do we have on the other side? Okay, we got to solve for delta v, right? So we got delta v, and that's just going to be this f dt integral divided by mass, right? So delta v, in the middle of this thing, if we say from 0 to 0.3, it says that the ball was incoming at a velocity of 22 meters per second. Okay, now let's look at the other side. We got to take this over, and we'll say we're looking at the same deal over here. So this is f dt, and then we got to add what's above it. So we're going to do the same deal. Second half, sum of f dt. So this thing, right, is f dt plus the previous f dt above it. We're going to do that from 0.3 to 0.6. So that goes here. Now that's our integral. We take this divided by our mass there, okay? And we get a V final of 4.6. So V final of 4.6, V initial 22.06. Now the energy in, that's going to be 1/2 times mass. Our mass is 0.5, right? We got 5.5 times V initial squared. All right, that's the energy in, energy out. This one will be V final squared. So then energy lost, that will be the difference of these energies. Okay. So we can do the same analysis for the elastic ball force, right? And in this case, it looks like we have the ball starts a contact at 0.022, so we would start here, and we would end the integration at this peak, 0.036 here. Let's make sure that's equal time. 0.058. So it looks like 0.058 minus 0.022. Half time is at 0.018. So then this thing is this plus 0.022. So half time is at 0.4, right? So we would integrate from here to here and then from here to here, right? We do the same exact type of analysis to get energy lost. Okay, so in the report, we need the pumped up ball, that's the elastic ball, and the flat ball. And go ahead and show all these calculations and how you got there. Please also include a plot of the force response you used, right? We have 5 of them in this force over time curve. Let's see, I think this goes to like 20. All right, so we have 1, 2, 3, 4, 5. We have 6 of them. And go ahead and do this analysis for at least 3, and then give us the energy lost for the 3 different peaks that you choose. Do that for both the force, flat ball, and the elastic ball. Okay.